Okay, so welcome back to wave equation solving wave equation using direct method. So last time we talked about stiff and inverting boundary conditions. We discussed that in the wave equation, the second step actually really defines whether we're going to have two waves or one wave. So I'm going to show you the MATLAB script hopefully in this video or maybe not, and it's going to be the next video. So we know that this is second order in time and space, so we need, because that's second order in time, we need two sets of initial conditions, one at time, let's say 0, and one at time 1. Then we use the time 0 and time 1 to calculate the time 2, because that's second order. We need two sets. So using these two sets, the one that you use actually in the second time step to calculate the, or to provide the initial condition, the second step is really important because it's going to tell us whether we're going to have two waves going left and right, or we're going to have only one wave going left or right. So, and we discussed this last time, that in a two-wave traveling, so the way to set up is when we set du dt equal to 0 at any point equal x in the second time step. If you assume that du dt is equal to 0, then any point time delta t gets information from time 0 at point x. So anything at point x is going to be transferred to the same point at time x at time delta t. So now we're going to have two waves. But if we just set the information at time delta t and point x is coming from the previous time step and the point on the left of this, then this is going to be a right traveling wave. If you put the displacement at point x and time delta t equal to or coming from the x on the right side of this point, then that's going to be the left traveling wave. So you're going to see what this means exactly when I show you the MATLAB script. All right. So one last thing I want to talk about in Leapfrog is, so when we set alpha equal to exactly 1 in direct method, we're going to show that why it leads to the leapfrog exactly and why we don't have any attenuation of the wave magnitude. So looking at the discretization of the wave equation using direct methods, where we use the central difference for the time derivative and central difference for the spatial derivative, because you're using alpha equal 1, then del t squared times v squared over del x squared, so these three cancel out, because if you multiply through by del t squared, then del t squared times this divided by that is going to be 1 anyways. So these three cancel out, and then the 2 uj n from both sides also cancel out. So what we're left over with is just n plus 1 and minus 1 on the left side and j plus 1, j minus 1 on the right side. Okay. Now we're going to use Taylor series on time on the left and then on the space on the right. So this is the Taylor series for the two terms on the left. This is the Taylor series for the two terms on the right. Like j plus 1 term is going to be j and then del x times times the first derivative of uj and then time plus del x squared divided by 2, the second derivative of uj, and so forth. And so the odd term cancel out because we have a plus del x here and minus del x here, and what we are left over is only the even power. So I think that should be the second derivative. Okay, so we got the uj, the second derivative, fourth derivative, and so forth. And same thing for the time derivative. We are only left with the even terms in the Taylor series. Then so we're gonna use we're gonna do a lot of cancellations here. The 2 uj cancel out from both sides, and then we use the condition that del t squared is equal to, like, from here. So because our alpha was 1, then del t squared or del x squared is going to be v del t squared if you cross multiply here. So we use this condition in here. We can relate del t to del x, and or we can actually change the derivatives You can change the derivatives from time to x, like d dt is going to be d dx. We can use chain rule, d dx, and then dx dt, which is dx dt is equal to v. So any time derivative can be related to spatial derivative times v. So any time derivative we have here, we can relate them to the spatial derivatives. Okay, so this is going to be v squared times, like here. So this is going to be v squared times the derivative with respect to x, and then del t v squared is going to be del x squared. So this thing is going to be del x squared divided by 2 times u and j, which is exactly this term, the second derivative. So again, this double quotes means second derivative in space, double dots means second derivative in time. 4 dots means fourth derivative in time, and this means fourth derivative in space. So anyways, we can relate the time derivative to spatial derivatives using this table, and we see that any time derivative is going to be del x times the spatial derivatives. And so by doing so, we can easily show that the left side is always equal to right side. All terms cancel out, so we are not left over with anything. That means, if you go back, means these two terms are exactly equal to these two terms, which means our discretization here is exact. There's no error in here, and that's why when you do this using direct method, you do not see any attenuation in the wave. Again, I'm going to show you how this comes about in a MATLAB script. So the last topic I want to talk about here is the implementation of the wave equation using using Leapfrog. And let's see, the last one we're going to talk about is going to be Lax-Windroff. So okay, so this is the 2D version of the direct method that we talked about. We have now 2 spatial indices I and j, where the I index represent the x derivatives, and then j index corresponds to the y derivative. And if you follow the 2-dimensional discretization of the wave, you get them two sets of alphas, alpha x and alpha y. So alpha x is going to be v dt divided by del x, and alpha y is going to be v dt divided by del y. And now our CFL condition in 2 dimension is going to be a combined non-dimensionalized version of velocity in the x and in the y direction. So that's why we have v squared del t over del x squared plus v squared del t over del y squared less than 1. So the total sum has to be less than 1. All right. So now we have the CFL condition in 2 dimension. So that is the direct method in 2 dimensions. Now going back to Leapfrog, and so we're gonna show you how we can discretize this wave equation in Leapfrog. So remember, we converted our second order differential equation to a first order system, where now instead of having u as the only unknown, we're going to have r and rs and then u, but the system is going to be first order. So we talked about how we can convert this into a first order system in terms of r and s. We converted this to a y vector, or d dt of y plus a times d dx of y is equal to 0. Now, because this is first order, we can write, we can apply the Leapfrog on that. So remember, where we use Leapfrog for 1-dimensional or for ODEs, that we're going to use Leapfrog for this PDE. Okay, so or in other words, we use Leapfrog for a scalar equation. Now we're going to use Leapfrog for the system instead of the scalar equation. All right. So before we jump into the Leapfrog discretization of the wave system or wave equation, the system equation, we need to do a little bit of derivation on the spatial and time derivative at half points. So this is the we need to know the r at point n. So this is r. We're gonna need r at point n and spatial coordinate j plus half. By definition of r, which is v du dx, we need to discretize this at n and j plus half. And that means we have to center this at point n, and then we just get derivative with respect to x, centering at j plus half. That's why we have j plus 1 minus j. So this is central difference about j plus half. We can do the same thing for s variable at n plus 1 half, because we need dt, ds dt. Or in other words, s was du dt, if you remember. And so when we do the discretization of the du dt for half time point and spatial coordinate j, then we're going to have fixed j, but then we center the central difference at n plus half. So average of n plus 1 and n is going to be n plus half. This is central difference about n plus half in time. Okay, so now we have discretization of j plus half and sn plus half. Then we use leapfrog. So if you remember, leapfrog is centering or using central difference in time and space. So this is central difference in time for a variable r, and this is central difference for a variable s about point j plus half. So basically we're discretizing the first equation here, which is dr dt is equal to v ds dx. And that's what it is. So this is dr dt, and this is going to be ds dx. And then that v goes into this alpha. Okay, so because this is central difference, means we're doing the time difference about n plus half. This is central difference in x. We're doing central difference about j plus half. That's why these indices are j plus half and these indices are n plus half. We do the same thing for s variable. S by definition is, if you go up here, ds dt is v dr dx, and that's what we have here. So this is dr dx, this is ds dt. Again, this is centered at n plus, this is centered at n, and that's why we have n here. And then these guys are centered at j, which we have in here. All right, so the last thing we're going to use is the definition of s, which is du dt. We're going to use central difference again, so it's going to be n plus 1 minus un divided by del t. And then on the right side, instead of having du dt, instead of having s, we're gonna center s at average of n plus 1 and j and n and j. So basically, this thing is jn plus half. That's exactly this guy. And basically, we put this at n plus half and j, and we discretize this at n plus half and j. But then central difference at n plus half and j is going to be n plus 1 j here and then nj. So the difference of these two gives you du dt, and this is going to be at n plus half, which is the average of these two, and then same j. All right, all we need is now we're going to plug in these this equation into, so we're going to plug in this equation in here, and whenever we need r, we're going to use that equation. So let's see what happens. So here we have n plus 1 and j equal to unj, and then instead of n plus half and j, we're going to use this equation, right? Where n minus 1 half j, we're going to use, we come back to here, basically. So for n plus half and j, we're going to use that, which is another n plus half, and n, we're going to move all the u's to the left side. That's why we get minus 2un here. And then, so that's going to be, we replace this in terms of u's. We need to replace, yes, we need to replace r also in terms of the u's. So for r terms here, we have to use the first equation here. So in the next video, I'm going to talk about the discretization